Hello, welcome back to Chapter 2, Atoms, Molecules, and Ions. I added a norm for us, which I think is really important. And that's the idea of ownership or agency and self-regulated learning. So for example, I know that when I go too fast, I'm prone to make mistakes. And so that is something that when I'm reflecting on my own learning, it's really important that I iterate or I make sure that I go back and slow down my pace. That's a great example of self-regulated learning. Part of adjusting to teaching the class and thinking about your success is me making sense of how you learn. But this is a partnership, and so you are also engaged in this, where you have ownership and agency. You have the ability to self-regulate your learning. So we're going to persist in creating a safe space. Questions are always welcome. We're going to work together to collaborate. That's going to be particularly true today when you take the quiz. And then we're going to iterate. We're going to take a risk and try again. So we talked about this warm-up problem last class, which was the level of carbon dioxide in the atmosphere. And I wanted to make sure that I was clear that there are multiple ways to solve this problem, but my point in sharing this problem was I really wanted you to think about what was reasonable. So here's another way that you can solve that problem, right? You just take your new value, right, and divide it by the original. That's going to give you 130.8. So then we would have to subtract 100. So 130.8 minus 100 would also give us that positive 30.8%. But here's my dilemma. Even when I'm given the equation, sometimes I mix up the order of subtraction. So what if I had calculated 317 minus 414.7 over 317? Well, that would have given me a negative number. And so I have to ask, is my answer reasonable? Well, if I go back to my graph, I know that having a negative percent change is not reasonable because as I look at this, it's increasing and it's increasing in a positive direction. So I know that this negative, right, doesn't make sense. So what I want us to think about, right, is less memorizing our answers. That's only going to take us so far. But being able to answer the question of, is my answer reasonable, right? Do my units make sense, right? If I were to estimate my answer, does that make sense? That's going to take us quite far. So the scientist that I wanted to share out about today is Peter Kalmu. He's a PhD data scientist at NASA's Jet Propulsion Laboratory. He also works at the Joint Institute for Regional Earth System Science and Engineering, affiliated with UCLA. And he's an author of Being the Change, Live Well, and Spark a Climate Revolution. The reason why I chose Peter as a scientist to spotlight is because his original work was really in engineering, but he is currently doing research in ecological forecasting, looking specifically at coral reefs and ocean acidification. And the reason I think he's an interesting scientist to look at is all of his training, right, was in one field, but he took all of that expertise and insight and is using it to solve problems in a different field. And so one of the things that sometimes happens is that as scientists, right, we encounter a problem and we're trying to think about how to solve that problem, and sometimes being able to transfer knowledge across disciplines really helps us to make sense of that problem. So if we think about designing and implementing methods of gathering information and data to answer a question, I want you to think about how you would interpret this data visualization. So what is this really saying? So we have the amount of water that's in seawater, and then we also know that seawater contains salt. And if I'm interested in the composition of that salt, that's where this blow up or this square starts to make sense of that. So sea salts include chloride and sodium, sulfate, calcium, potassium, magnesium, and some other minor constituents. These are the quantities in relation to 1 kilogram of seawater. So here's my question. What is the percent by mass of sodium in seawater? If there's 10.78 grams per 1 kilogram of water. And so if we think about how we might calculate that, one of the things we're going to have to do is reconcile our units. So if I have 10.78 grams of sodium and I have 1 kilogram of seawater, right, I'm going to need to do a conversion. And notice here, right, you actually have two different choices, right? So your choice is you can convert your grams of sodium to kilograms, or you can convert your kilograms of seawater to grams. The idea is that you ultimately want to convert to a unitless ratio. Notice the math is the same. So it's two different ways of solving the problem, but you should get the same answer, which when I were to divide 10.78 by 1,000, I get 0.01078. And notice this is a unitless ratio, right? That ratio is important because ultimately it's going to end up being a percent. So if I were to multiply that by 100, right, then I get that it's roughly 1.078%. So if I think about my original question, right, I have 4 sig figs here, I have 1 sig fig here. So it's fair for me to say that my answer is roughly 1%, right, of seawater is sodium. So let's talk about learning outcomes. We're going to wrap up chapter 2 today. And this again is, right, naming molecules and ionic compounds and acids, and then correctly writing out the formulas for ionic compounds, molecules, and acids. And then we're going to start taking a look at chapter 3, where we use mass percent as a conversion factor, and we're going to start to think about converting between mass and number of particles. The science practices that we're going to use today is asking questions and defining problems, analyzing and interpreting data, constructing explanations and designing solutions, and engaging in argument from evidence. You're going to notice that these 4 science practices come up again and again and again. And our goal is that we become adept or skilled at using these practices, no matter what type of problem we're solving. So as a reminder, you're going to do a quiz today, and hopefully for your quiz, you have available your own flowchart or decision tree. If you're not sure about what that could look like, there's an example for you to check out here that was created using Coggle, which is technology or software that you can use to create your own concept maps. But you could also create it by hand. It's entirely up to you. So the thing that's not on the quiz today is naming acids, because we haven't talked about those yet. So let's talk about how we name acids. Acids are named based on their anion, the ion that's attached to the hydrogen. So in simple binary acids, one ion is attached to hydrogen. Names for such acids consist of the prefix hydro, the first syllable of the anion, and then the suffix -ic. So for example, HF would be hydrofluoric acid. HCl would be hydrochloric acid. HBr would be hydrobromic acid. HI would be hydroiodic acid. And H2S would be hydrosulfuric acid. So binary acids, though, aren't the only acids that we have to name. There are also complex acid compounds that have oxygen in them. For an acid with a polyatomic ion, the suffix -ate from the ion is replaced with -ic. So polyatomic ions that have 1 extra oxygen, compared to the typical polyatomic ion, have the prefix -per and the suffix -ic. And then polyatomic ions with 1 fewer oxygen have the suffix -us. Ions with 2 fewer have the prefix hypo and the suffix -us. So what does that look like? Well, here are some examples. Sulfate, sulfite transitions to sulfuric and sulfurous. Nitrate and nitrite, right, becomes nitric and nitrous. Here are some examples of how you would take the anion name and convert it to the acid name. And again, you'll have the opportunity to practice this. We will work on this together as a review in class on Monday, and then you'll have the opportunity to practice naming acids in the quiz on Wednesday next week. So if we think about transitioning to chapter 3, this is the composition of substances and solutions. We have a couple of things we want to review. We want to review how we find atomic mass. So on your periodic table, you should be able to find the atomic mass for chlorine. And remember that molar mass is reported in grams per mole. When you're calculating a compound's molar mass, we want to make sure that we add the molar masses of each atom in the formula. So for example, the formula mass could also be known as the molar mass, right? Capital M, or FW, which stands for formula weight. And, right, we can practice calculating an example. So for carbon dioxide, That would be 12.01 grams per mole plus oxygen, of which we have 2. So 2 times 16 would give us 32. So the total would be 44.01 grams per mole. Now, here's what's really interesting about that. We're going to use that formula weight now to figure out mass percent composition. So you can find this experimentally from elemental analysis, or you can calculate it from a chemical formula. The easiest way to calculate this is just to take the mass of the element, say for example in this case carbon, and divide it by the compound mass of CO2. We multiply that by 100. But notice, right, these units are in grams, so it's a unitless ratio, right? But what if you didn't know how to find this, right? You could also make an assumption. So let's say you assume you have 100 grams of carbon dioxide. Well, then you could convert that mass in grams to moles. You can convert your moles of CO2 to moles of carbon. You can convert your moles of carbon to your grams of carbon, and then you could calculate your mass percent. So you can either do it directly from the mass as reported in the periodic table, or you can make an assumption that allows you to calculate out and cancel your units. Then you would just replace, in this case, your mass C and divide by your total mass, and then multiply by 100. So we're going to practice this because it's also using mass percent as a conversion factor. So you could look at the mass percent of an element in a compound, which is equal to the mass units of the element divided by 100 mass units of the compound. So here's a great example of that. That's using mass percent as a conversion factor. So if you had to calculate the mass percent of copper in copper sulfide, you would have to do 2 times the molar mass of copper divided by 2 times the molar mass of copper plus the molar mass of sulfur. Then you would multiply that by 100. So that gives you 79.85% copper by mass. Well, what if you had 1.3 kilograms of copper sulfide? Well, then you could take your copper sulfide and multiply it by this ratio, 79.85 per 100 kilograms of copper sulfide. And that would give you the amount then that you have in kilograms of copper. And again, if you were paying attention to your sig figs, right, you would have 1.0 sig figs. Okay, let's think about how we could use that in our science practices. We're going to argue from evidence. Here's an example. We're going to pick one of the following chemical formulas and name it. The name is our claim. Then we're going to provide evidence. So our evidence is that HNO3, because it has the oxygen, is a complex acid. We know the rules for naming complex acids are 8, the anion, becomes ic acid. So the answer ic replaces the 8, and then we add acid. And that's how we would name nitric acid. So you can use your flow chart, and that's really what allows you to provide this claim evidence reasoning statement. Well, what about calculating the percent of oxygen? So I'm going to think about, right, my percent. So I'm going to choose nitric acid, right, because that's the one I named. And I'm going to think about, right, the molar mass in total of nitric acid is 63.01 grams. The mass of oxygen, I have 3 oxygens. So 3 times 16 gives me 48 grams. So 48 grams divided by 63.01 grams gives me 0.761 or 76.1% of oxygen in my nitric acid. If you want some additional practice with this, I highly recommend you check out S Cubed, or we'll be practicing these in discussion. I want to make sure you take 5 minutes to turn and talk with a partner or to reflect for yourself your goals, your metacognition, this is your thinking about your thinking, and reflecting on your own learning. Next Monday, we're going to be thinking about the composition of substances and solutions, wrapping up chapter 3. And that means that we're going to make sure that we've done our reading to be ready for chapter 4. Thanks again.